Hello, I'm Timothy Purcella here with my Math 1325 class today, and we're going to graph a third degree polynomial function using our general factoring strategy that we developed in class. So first of all, we'll find the x-intercepts by setting x, we'll find the y-intercepts. Pardon me, it's the first thing we'll do. That's easy enough, okay? Finding the x-intercept, that may be more involved than what we want to do. It's possible we'll have to decide, oh, that's too much work. So I say find x-intercepts if it's not too much work. Then use the first derivative test to find local extrema and determine concavity using the second derivative, and then we can draw the graph. But remember, I said that after the first three steps, if the problem just said draw the graph, after the first three steps you could get a very good picture drawn. Okay, so concavity for polynomial functions takes care of itself when you're drawing the graph. So here's the function we're working with. Y equals, this is number 3, let me write that down. This is number 3 for the students enrolled in my class this semester, fall 2014. And we'll go through our little graphing strategy. The first thing we'll do, we'll find the y-intercept by setting x equal to 0. So setting x to 0, we're going to get y equals 0 minus 0 plus 0 minus 3, so a negative 3. So the graph is going to contain the ordered pair 0, negative 3. The graph is going to pass through the y-axis at negative 3. Second step, we'll find our x-intercepts if it's not too much work. That's what I mean if I say if it's not too difficult. If it's not too time-consuming, find the x-intercepts. To do that, we set y equal to 0. So we have 0 equals x cubed minus 15x squared plus 75x minus 3. What do you think I'm about to decide here? It's too time consuming, okay? This is too time consuming, so I'm going to say too time consuming. It's not worth the effort. So I'll just skip. I'm not going to find the x-intercepts. Third step, I find local extrema using the first derivative test. So finding y prime, I get, differentiating, what am I going to get? 3x. Keep going, 3x squared minus 30x plus 75. And what do we do now? Set it equal to 0. Good. And here's something I can do. What I'm about to do, I can do to the equation. I can't do it to the derivative, okay? The derivative's a function. But to the equation, I can say, okay, there's a common factor of 3. I'm going to multiply both sides by 1/3. Multiplying by 1/3 is the same thing as just dividing by 3. So I'm getting 0 equals x squared minus 10x plus 75 divided by 3. I was just trying to see if y'all were following what I was doing. And this is factorable. If it weren't factorable, we'd have to use the quadratic formula probably, and we'd get something, irrational critical numbers, but the process would still work. And this is very nice. What are we going to have here? Just a 5. So there's only one critical number, or one critical number. Is x equals 5. Now what do? Draw your number line. We draw our number line. Well, let me change colors. I'm going to draw my number line. The only number I have to label on there is 5. And so I'm looking at the sign of y prime. To the left of 5, what do y'all want to test? 0 is an easy number to plug in. So testing 0, we get y prime equals, and remember this is the thing you're plugging into. That would be a 0 minus 0 plus 75. That's positive, so increasing. What about a number to the right of 5? What easy number do you think I'll use to plug in there? 10. 10's easy for me to plug in. So let's see here. I'll plug in a 10. That'll give me y prime equals, that would be a 300 minus 300 plus 75. What sign is that? Positive as well. So the function's still increasing. It was increasing. It leveled off a moment at 5, and we thought it was going to start decreasing, but it didn't. What did it do? It kept on increasing. So what do we conclude about local extrema? Do we have a local maximum? No. Do we have a local minimum? No. There's no local extrema. Step number 4. Determine concavity using the second derivative. So we'll have to find y double prime. We'll determine concavity, but even without that, we could still get a pretty good picture drawn, okay? But we'll go on to step number 4, concavity. Let's see, do I have room down here? Yeah, I have room down there. Here's step number 4. Y double prime equals 6x minus 30. Set equal to 0. And what are we going to get? X equals 5. That's the same number we got as a critical number, but we didn't have a local extreme value occurring at 5. Maybe we're going to have an inflection point. Maybe concavity will change at 5. Draw your number line. There's 5. A sign of y double prime. What do y'all think of all these colors that our secretary got for us? I even have an orange pen around here somewhere. And my purple pen? Yeah, there. Maybe. Okay, so what do you think we'll test to the left of 5? 0. Testing 0. Oh, I'm running out of room. We're going to get a y double prime equals. My brother says we need to get manicures since our hands are under these cameras so much. I don't think anyone's really looking at our hands. What do you think? Unfortunately, I can think of better things I want to spend my money on, I suppose. So, plugging in 0, what are we going to get? Will y double prime be positive or negative? Negative. So it's concave downward. To the right of 5, what do you think I'm going to test? 10. So we'll have y double prime equals, that's going to be positive then. That'd be a 60 minus 30, positive. So concave upward. Okay, so I think we're ready to, so we do have a point of inflection. The point of inflection occurs when x is 5. So I'm going to have to come over here, the next page. Okay, so you know what I'm going to have to do? I'm going to have to tear this out. So invariably I'll drop it and then not be able to find it. So here we are, there. We have a point of inflection. and it occurs when x is 5. So where do we plug that 5 to determine the y value? Into the original function. So plugging 5 into the original function, let's see, plugging 5 in right here, 5 cubed is a 125 minus 15 times a 25 plus a 75 times a 5 minus 3. That gives us a y value. I'm getting 122. Could have been some small number like 7, could it? Had to be 122. And now we're ready to draw our graph. Let's see. I had some graph paper in my office, but I didn't bring it, so I was too busy getting all my color pens together. So there. We have a point of inflection. First of all, let's see, what ordered pairs do we have? We have the y-intercept. It's going to pass through the y-axis at -3, so right there. And we know that there's a point of inflection. Normally, I don't bother labeling points of inflection, but it's the only other point we have. And I feel like we need to label something. So way up here, I'm just sort of changing the scale as I go. There's the point 5, 122. Is that what we had, 122? Yes. We know the function is increasing, and then when it gets to 5, 122, it levels off a moment, then it starts increasing again. We know the graph is concave downward to the left. To the left of 5, it's concave downward. To the right of 5, it's concave upward. But we also know that this is a polynomial function, so that means it's a smooth flowing graph. So it's going to go, it's concave downward. Okay, like that. You know, I'm going to take a different color. There, make it stand out better. So it's concave downward. It's going up. It levels off there a moment, and you think it's going to change directions, but then it continues going up. For my graph, it's increasing, it levels off a moment, and then it starts to decrease. But in reality, that's the only way you could have gotten it. Even if we hadn't tested concavity, even if we hadn't done the concavity test, in order for it to level off there, the only option is for it to concave downward. Derivative is 0 right there. That means a horizontal tangent line. Then it continues upward. If it didn't if it were concave downward and then concave upward, you wouldn't have a derivative of 0 occurring there. So you it would be such a sharp point. I would expect an undefined derivative or something. Any questions there? But even if I hadn't found concavity, this is how I would have drawn the thing. And we know the basic graph of y equals x cubed. In previous math classes, we saw the graph of y equals x cubed. It looked like that. Concave down and then concave up. It's the same basic shape, concave down and then concave up. But the point where it levels off has been translated to the point 5, 122. Any questions? Okay, now let me see. This problem is printed out, so let's come back here. Let's see. Let's answer what we have. Let's see. What are the coordinates of the relative maximum? What do I select there? Was there a relative maximum? No, so there's no relative maximum. It should say there's no relative maximum. My math lab's messing up there, okay? What about the coordinates of the relative minimum? There's no relative minimum. It should say that word relative or local. What about the coordinates of the inflection point? Do we have one of those? Yes, that was the point 5, 122. and draw the graph. Let's see. No, that's not got. Okay, well, let's see if we can find. This is, what number was this? Number 3? There it is. Okay. Here's number 3. You're going to have to use your bionic eye to see this graph. Okay, so there. A, B, C, or D. Let's see if I can do this. There. Which one? A, B, C, or D? Which one does it look like?
B.
I think B is the only one that is remotely close. Graph B. Any questions there?
I have a question.
Yes.
Where can I see the first step result?
The first.
0 and the -3 it's not showing in the graphic.
Oh, well, it's showing it here. They're not really showing. That's just, it's sort of, I mean, I graph that. That's what I do to get the graph drawn, okay? But they're not.
Past the here, right? Past the.
That's where it's passing through. But this graph, the scale is so small. To me, it looks like, when you look at this, looks like it's passing through the origin, isn't it?
So
But
from the graph, it looks like it passing 0 and the 0.
that's right. But we know in reality it's passing through 0, -3. But look how little bitty the scale is.
Okay.
That's one of the problems with that small scale.
Okay.
Yeah. And I don't think you'll see them finding the, showing the intercepts on any of the graphs. That's just what I do to get a good picture drawn.